2. L'Hopital's rule. Indeterminate form 0 over 0. If functions f of x and g of x are both 0 at x equals a, then the limit as x approaches a of f of x over g of x cannot be found by substituting x equals a. The substitution produces 0 over 0, a meaningless expression known as an indeterminate form. So if we plug in 0, let's say, or plug in any value, and we get 0 over 0, that doesn't mean the limit doesn't exist just because there's 0 in the denominator. We can use what's called L'Hopital's rule. Suppose that f of a equals g of a equals 0. In other words, the top and the bottom function are both equal to 0 when we plug in a value. That f prime of a and g prime of a exist, and that g prime of a still does not equal 0. Then, the limit as x approaches a of f of x over g of x is equal to f prime of a over g prime of a. In other words, we can take the derivative of the top and the bottom. Example 1, an indeterminate form 0 over 0. Estimate the limit graphically and then use L'Hopital's rule to find the limit. We'll just find the limit. When we plug in 0, we get the square root of 1 plus 0 minus 1 over 0, which is equal to 1 minus 1 over 0, which is the indeterminate form 0 over 0. That means we can take the derivative of the top and the bottom and then plug 0 in. So we have the limit as x approaches 0 of 1 over 2 square root of 1 plus x. That's the derivative of the radical. The derivative of negative 1 is 0, and the derivative of x is 1. Now that's equal to 1 over 2 times the square root of 1 plus 0, which is 1/2. Theorem 5, L'Hopital's rule, stronger form. Suppose that f of a equals g of a equals 0, that f and g are differentiable on an open interval I containing a, and that g prime of x does not equal 0 on I if x does not equal a. Then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime over g prime of x. In other words, if you keep getting an indeterminate form, you can just keep taking the derivative. Applying a stronger form of L'Hopital's rule. When we plug in 0, we got to see that we actually do get an indeterminate form. We have 0 over 2 over 0 squared. This part will be 1 minus 1, that's 0, minus 0 over 0, so we get an indeterminate form, meaning the limit still could exist. Now we have the limit as x approaches 0 of, we have 1 over 2 square root of 1 plus x, and then minus 0, and then minus 1/2, and that's going to be all over 2x. Well, let's see if we still get an indeterminate form. If we plug 0 in here, we get 1/2 minus 1/2, that's 0 on top, over 0 on the bottom. So now we can do L'Hopital's rule again. We have the limit as x approaches 0 of, now this is 1/2 1 plus x to the negative 1/2. So this is going to be negative 1/4 times x 1 plus x to the negative 3/2. The derivative of 1/2 will be 0, and in the denominator we have 2. Well, that's equal to 1 over, actually negative 1 over 8, 1 plus x to the 3/2. And we're still doing the limit as x approaches 0. When we plug 0 in here, we just get negative 1/8. Evaluate the following using L'Hopital's rule. The limit as x approaches 0 from the right of sine of x over x squared. Well, the sine of 0 is 0, and 0 squared is 0, so we get 0 over 0. Let's do the L'Hopital's rule. So we have limit as x approaches 0 from the right, and we're doing L'Hopital's rule here, of cosine of x over 2x. Now when we plug in 0, we get 1 over 0, which you would think is undefined, but in this case with limits, it's actually going to be positive infinity. We are approaching 0 from the positive side, so this could be 1 over 0.00000001, which is going to be a very big number. And the closer we get to 0, the bigger this will evaluate at. So this is shooting off to infinity on the positive side, so positive infinity. Let's look at B. We get 0 over 0 again, so we're going to do L'Hopital's rule. we have the limit as x approaches 0 from the left now of cosine of x over 2x, which is 1 over 0, but this time we're approaching on the negative side. So this is like having 1 over negative 0.00000001, which would be a negative very big number, which is negative infinity.